Professor Nassif Ghoussoub got his PhD degree in 1979 in Paris. And then after that, he worked on nonlinear functional analysis and PDE, and did a lot of the important contributions. And for example, one of them, here I only mention one of them. For example, in the joint work of Nassif and Changfeng Gui, they got a very brilliant breakthrough on the George conjecture, completely solved the conjecture for the dimension 2, and also made a substantial progress for the conjecture up to dimension 5. And this is highly evaluated by the mathematical community. And also, Nassif is the founding director of the Pacific Institute of Mathematics, also the founding director of BIOS, of the Banff International Research Station, and made great contributions to the mathematical community. And because of these contributions to mathematics and the mathematical community, he already obtained a lot of the prizes, awards. So let's welcome Professor Nassif Ghoussoub.
Thank you, Yiming, and many thanks for the organizers of this wonderful Congress. Many happy returns. Many thanks to the planning committee and the scientific committee and the local arrangement committee. I think it's a wonderful event. So we had some great pure math talk in this Congress and great applied math talks. And here it's a different type of talk because I'm a pure mathematician, as most of you know, and I'm trying to tackle or understand some applied problem. And so my talk should be viewed in this way about pure mathematicians. Pure mathematicians often surprised how mathematics work in understanding math in applied or a model, and also the frustration that we've had. So it's been a rewarding experience because mathematics could do something, and secondly because the model allowed us to deal with new type of problem of questions mathematicians don't deal with usually. It was also frustrating because, as you see now, that there are some very basic aspects of PDE or analysis that we still cannot do anything about it. And this is a bit humbling. So let me talk about this model. Actually, 5 years ago, a bunch of applied mathematicians at the University of British Columbia and engineers came to me with this model dealing with MEMS, which is Micro-ElectroMechanical Systems. I didn't know anything about this then. And they had lots of numerics, lots of simulations and conjectures, and they want to see whether mathematical analysis can do anything. And surprisingly, 5 years later, we have lots of progress. What am I doing here? So the 5 years project started in 2004, so it was a bunch of my students and postdocs, Craig Cohen, Pierpaolo Esposito, Eugene Gouault, Amir Mouradifam, all of them looking for jobs. And this culminated in a book that will be appearing very soon as lecture notes at the Grand Institute, which is the title of this. And the authors of the book are only with Esposito and Gouault, who just finished, who already finished their PhDs, not others. So this is a list of applications of MEMS. One reason, which are at the roots of microsystem technology. One reason I'm listing all these applications is to impress you, of course. The second reason, what I want you to get out of this is that, when you could see from micro pumps and accelerometers and micro switches, that the system really is supposed, it should imply that snap through, that something should snap, some or rupture. So there's singularities in the system that you would like them to be there. Now, the very, very, very simple model is the following. And so we have a membrane, elastic membrane, which is above a ground plate, which is a rigid ground plate. And the membrane is fixed on the boundary. The upper surface is coated by some conducting film. And then you apply voltage, and this membrane is supposed to deflect toward the ground plate. So the larger the voltage, so it deflects and gets closer to the ground plate. At some point, it hits the ground plate, and there's a snap through, so the system stops, which is really what it's supposed to do. So it's a very, very simple model. And so here you could see, so this membrane on top, and this is the ground plate here. The distance between the membrane is d. It's going to be 1 in my talk. So I guess this is exactly what I just described. Okay, so I'll leave it here. So the point is that one can see easily that, okay, that if the voltage goes beyond a certain point, then you have the snap-through, and you would like, and this is a very important, it's called the Pullin Voltage. It's a very important parameter of the system that you'd like to evaluate. Now, how do you model this? Now here, as usual, as applied mathematicians know, there are many models. The more accurate the model, the more complicated the equation. That means we can't do anything about it. And this is one of the basic models. And U is measuring the height of the deflection at time t above the position x, UTX. So what are the forces involved? So here you could see the kinetic energy here. This is a damping force, coming from damping force. Let's look on the right-hand side. Okay, C and V are constants for now, but this inverse square, so U plus D is a distance between the deflected membrane and the ground plate, which is at position negative D. Okay, so U plus D. So this nonlinearity is inverse square. And this is coming from the Coulomb law of the distance, the electrostatic force between the membrane and the ground plate. Okay, so the inverse square is coming from, okay, so U is a position at the time Tx, and D is a fixed distance. So this is the nonlinearity. Now, the Laplacian here, as I said, it's an elastic membrane, so essentially it's a stretching, it's coming from stretching energy, which is essentially proportional to the change of the area, surface area of the membrane. So when you linearize it, you get the Laplacian. T is a tension constant. Now here you have the bi-Laplacian, but here, because you're allowing bending at some point, which is proportional, so this term comes from the bending energy, which is proportional to the change in curvature. So when you linearize it, you're going to get the bi-Laplacian. So these are the various energy terms, and when you equate them, so you have the electrostatic force, and then playing against all the mechanical forces of membranes. When you put them together, you have this. The first boundary condition saying that the membrane is fixed or the microplate is fixed on the boundary. Okay, and this is the initial condition. Okay, so this is really what the model gives you. It's a very, very simplified model because essentially assuming that the deflection only goes in the vertical direction above a point X and not going in 3 dimension, and it becomes a much more complicated system, von Karman system, that we don't know anything about. So even with this simplified model, as you see, it's quite complicated, and there's lots of mathematical analysis to be done. So first, good mathematician, let's start with the stationary equation. So stationary equation, that means we don't have the time component. So you have this force order linear equation with this nonlinearity, which is a new nonlinearity. It's 1 over u squared, essentially. And as you know, this is a new linearity, relatively new, because mathematicians are used to the Yamabe problem, Laplacian u plus u to the power p is equal to 0. We are used to power nonlinearity. So this is an inverse power nonlinearity. So this is the force order. Now, let's even go simpler case. Let's assume that the membrane is totally elastic and we don't have bending, so we don't have a force order because we love the Laplacian. The Laplacian, we understand. We don't understand anything else, unfortunately, as well. So if you suppose the bending constant is 0, then you have this equation. Okay, now this equation is a typical nonlinear eigenvalue problem that we should be able to handle. And sure enough, we could handle this, but you will see that even just the simplest part is a source of very, very rich, a very rich source of very nice mathematical problems. But notice the difference between these two equations. Here, the second one, I put 2 here to say that's second order, and this is 4. Here, the domain is different, is any domain. I did not specify. While here, I'm talking about the ball. Why? Because the bi-Laplace, even though we understand the Laplacian very well on every domain, but for the bi-Laplacian, we still don't know anything about it unless we are working on the ball. Mostly the maximum principle. Okay? It's because it satisfies the maximum principle on the ball, and that's why that's the only case where we can do something. And I think that this is a major challenge for analysis. That, something needs to be done about the bi-Laplacian. We should understand a bit more what's going on. And you will see at the end that we have some recent progress in this direction. So now, why is it important that we work on a general domain? And yeah, I did not talk about this function f here, f of x. Now, if f of x is equal to 1, that's a homogeneous case. The membrane is just homogeneous, there's no changes. But the engineers want to play on 2 things. First, the shape of the membrane, the geometry of the membrane. Should it be circular, rectangular, or other shapes to maximize or minimize certain parameters that I will be talking about. They also want to play with the structure of the membrane. They don't want it to be uniform. They want to change various parts of it, again, to play with these parameters. So that's where f of x comes in. So this f of x is a permittivity profile. It's called the permittivity profile of the membrane. And omega is the domain of the membrane. So here, notice that I left it f of x equal to 1, because even then, very little we know very little. And then the domain is circular. We cannot do. That's all. This is the only case where we can say something. And I really think it's depressing when you think about the huge mathematical structure we are developing, and we still cannot deal with an equation like this one, but on a ball. So these are the stationary equations. Now, the dynamic case, no one has touched the hyperbolic case, which means the case when we have a second derivative here. Okay, so this is, no one had dealt with it. So we are assuming now it's a very, very tiny thickness, so this is 0, so that we can deal only with the parabolic part. So we do deal with the parabolic part, and we have, well, I'm going backward here. So this is the part that we understand relatively well, and we have some results. But as you see, this is a very, very simple case, which is not acceptable. Okay, what do we deal with? If lambda is 0, if lambda is small, you know that there are solutions. If lambda is large, engineers know that there are no solutions. In other words, what does it mean there's no solutions here? Remember the equation. See, when U hits 1, see, I changed now. Now the ground plate is on top. Okay? So I'll still be talking about touchdowns. But the ground plate is on top, so that the solution is positive between 0 and 1. Okay? So when the solution hits 1, then the system breaks down. Okay? So this is why the... So for each lambda, for each voltage, we see whether we have a stationary solution. And this is classical. You can define the supremum of lambda such that the equation has a solution. See, this is a second-order equation. This is the first-order equation, but on a ball. Okay, so you can define the same number. And you can prove that there exists maximal lambda star, such that below it there is one solution, above it there's no solution. And what does it mean? That means if lambda small, you have stable deflection, lambda large, and you have the snaps through. And this is called the Pullin instability. And when lambda is equal to lambda star, this is a critical case. One would like to know what happened then. So lambda star depends on the domain, on the geometry of the domain, and depends on the permittivity profile. So in some systems, you would like to maximize the Pullin voltage. You would like the system to work for as large voltage as possible. In some systems, like security systems, you would like it to be as small as possible. You want the snap through to happen quickly enough before some disaster happens. So you'd like sometimes to maximize lambda star. So you'd like estimates on the Pullin voltage, function of the geometry of the membrane and the permittivity profile. And here it was interesting because engineers came with tons of calculations and experimentations about numerics. And it's very interesting that, well, before I get to this, so what does it mean here? Even though one has to prove it, but essentially we are saying that for each lambda, there is a solution, okay, up to a Pullin voltage lambda star. But one can notice two different situations. Here at lambda star, at the very end, this is 1 here. Infinity, one is infinity in this problem. Okay? So this extremal solution here at lambda star doesn't arrive to 1. So it's a regular solution here. If the solution is below, strictly less than 1, that means we have regularity. In this case, it touches 1. So this graph, this is the infinity norm, the sup norm of the solution, while here is the voltage. Okay? So you have two cases that can appear, either at this limiting case. But this limiting case will depend on the dimension and will depend on the permittivity profile. We'll see. So, for example, first, you would like to have lower bounds on the Pullin voltage. And you see some papers where they say, they do lots of numerics, and they say that Pullin voltage, the more round the membrane, the lower the Pullin voltage. Experimentally, they realize that there is some isoperimetry, that the circular membranes have the lowest extremal voltage. And this can be proved, that the Pullin voltage for a domain, so suppose F is equal to 1, is always bigger than Pullin voltage for a domain with the same volume. Okay, so if you rearrange the domain, so you can prove it, and because of that, you can deduce some lower bound for the Pullin voltage function of here the volume of the domain and the volume of the Euclidean ball in dimension. This is in dimension n. These are harmless. This is because for n equal 1 and 2, one of them is bigger than the other one. So you can prove lower bounds, and then you can prove upper bounds. I mean, they're not hard, just integration by parts and Pohozaev inequality, etc., but Pohozaev identity. So for example, you can prove the first upper bound for the Pullin voltage, which is much better than anything you obtained experimentally. And it's a function of the first eigenvalue of the Laplacian on the domain. So does that mean this reflects the geometry of the domain? Mu omega is the first eigenvalue. Okay? And F is a permittivity profile. Now, why you need both? Because in the first one, if F is equal to 1, this is fine. But sometimes you would like to allow permittivity profile which are 0 at some point. Okay? So if the infimum of the function of the permittivity profile is 0 at some point, then this doesn't make any sense. So you can replace this estimate by another one here, which is the integral of F times the first eigenfunction. Okay, so it's average. So even if F hits 0 at some point, this average will make sense. So then this will replace this. But you have situations, you have simulations where they're not comparable. In some cases, this is better than when both of them make sense. So a good estimate for this is still need to be done. There's another estimate that you can obtain for, what I'm trying to say is that you can do some simple mathematics, relatively simple. You get estimates that gives you, that are pretty satisfying and much better than the numerics that one get by doing just numerics. And these are questions that we wouldn't have asked ourselves to do if it wasn't for a requirement of the engineers that they want estimates. We can also look for the simplest permittivity profile to change the structure of the membrane. So you put X power profile, X to the power alpha. This is a place where it's 0 at some point of the membrane. And you try to see the dependence on alpha. And here it's very strange. For example, in dimension 2, you can prove this exact formula. And numerically, they notice that in dimension 2 and a circular membrane, if you increase alpha, then the Pullin voltage changes in alpha in a certain way. But I'll talk about the Pullin distance. But then you'll have a boundary layer. The solution becomes boundary layer as alpha goes to infinity. And I'll tell you why a bit later. But you can prove exactly the dependence on alpha. And here, and asymptotically for other dimensions. Now, of course, you don't care about the dimension 8, but we do. Mathematicians do. So you see in dimension 8, bigger than 8, you can compute exactly what this Pullin voltage is. And for alpha as well. But this is a story that I'll be talking about a bit later. So these are estimates that, okay. Now, So I showed you already a branch of solutions. Now, this is a minimal branch of solutions. What does it mean, minimal? These are the solutions that are lower than any other solution if they exist. So it's a point-wise minimality. But we'll see later that there will be higher branches of the solution. So how would you like to classify the higher branches? So here you have a spectral classification in terms of linearized operator. So if you have a solution U, so this is the linearized operator for the second order equation. For the fourth order, this will be. So you'll say that the solution is stable if this operator is positive definite. Okay? First eigenvalue is positive, if you will. So, and one can prove that minimality in terms of pointwise is the same as minimality, meaning that there's no negative eigenvalue. Okay? So, but then you might have solutions where the linearized operator is not positive. It has a negative space. So you can try to find the dimension of the negative space, and the dimension, if it's finite, is the Morse index of the solution. Okay, so so you can count the negative, the dimension of negative space for the unstable solutions, and you call it Morse index. So this is a minimal branch, and one can prove that it's increasing in lambda up to lambda star, but you have two situations. So lambda star, the Pullin voltage, we already defined it as the maximum voltage for which there is a solution. But then here, there's another characterization in terms of the spectral characterization. Here, the first eigenvalue, all these are stable solutions, as we said. These are minimal branch. So the eigenvalues are positive. But as lambda increases, the eigenvalues are decreasing. And then when you hit this point here, the eigenvalue, the first eigenvalue of the linearized operator is 0. Okay? This is a point, the first time where it becomes degenerate. Okay? So this is where the first eigenvalue becomes 0. And then we're going to have, okay. Now, the Pullin distance, they are interested in the Pullin distance. What's the Pullin distance? Here, in this situation, you get the Pullin voltage as a maximum of the system can if you're here, you measure you take the infinity, the height of the solution. It's strictly less than 1. So you would like to know this is the maximal steady state of the system. So you would like to see how far you are still from this ground plate. Right? So they're interested in an infinity norm of the extremal solution. It's called the Pullin distance. Okay? The Pullin distance is an infinity norm of the extremal solution, which is the Pullin voltage. Here, in this situation, obviously the Pullin distance is 1. Okay? While here, Pullin distance is not. So they're interested in the Pullin distance, which is an infinity norm of the, and here you can do some computation. So the Pullin distance, again, depends on the domain, on the permittive profile, on the dimension. We can do some computation. And here's an estimate. Suppose f is equal to 1. Then you can prove that for any domain, the Pullin distance is at least equal to 1/3. This, you do it because you're doing mathematics and you try to estimate, and then some cancellation, and all of a sudden 1/3 appears. And then, much later, you read in an engineering book, and there's a paragraph that says, well, the rule of thumb is that the Pullin distance is essentially 1/3 of the distance between the membrane at rest. And this was we proved this estimate before we knew that the engineers were noticing this 1/3 appearing between. But it can be done with simple mathematics, but nice simple mathematics. So now you can also estimate mathematically here the Pullin distance for dimension 1, dimension 2, higher dimension. Now, why should you be interested in 0.49 and 0.55? They're not interesting. But the proof is the following. You would like to prove that the solution at the Pullin distance is regular. So to prove it's regular by standard estimates, you would like to prove it's strictly less than 1, the infinity norm. Right? That's how you prove it's regular by elliptic estimate. So you are used to do this. You use energy estimates, combine them with Sobolev estimates, etc., and to prove that the infinity norm is strictly less than 1. But first you prove LP estimates. But you want exactly the infinity norm. You don't want it just to prove it's strictly less than 1. So you try to chase the constants. Constants in the energy estimates and the Sobolev estimates, etc. So you chase the constants because they're interested in how far you are from 1. You chase the constants, and then you get this kind of estimates. So the theoretical work that you do anyway to prove regularity, if you just chase the constants, and then you get estimates which are very, very good estimates compared to the numerics. So that's what I'm trying to say, that they're not much different. Proving regularity for the extremal solution and estimating the infinity norm, they're not different. Okay, now here for n is equal to 2, that's a very interesting situation where you could prove what they have been noticing, that if you take primitive profile, which is power-like, and then when you increase alpha, the infinity norm is still the same. So the solution keeps changes, but its infinity norm is still the same. It doesn't change as alpha goes to infinity. That means you're developing a boundary layer. Okay, it's stretching. And that was very surprising. And one can prove this mathematically. Why is this happening? That's a scaling argument. Okay? So the primitive profile doesn't depend on alpha. Okay, so these are, but the true story is the following. At the very beginning, when we got this model, I asked my student to do some simulation in the radial case. Radial case is ODE. ODE, you can do something. And then he got this picture. And this is the branches of solutions. This is a bifurcation diagram. So below here you have the voltage, and on top you have the infinity norm of the solution. Okay, so for each lambda here, there's a solution, let's say here, and this height here is the infinity norm of the solution. So realize that there are 3 shapes. For dimension 1, you have this branch. Okay, at lambda star is strictly less than 1, and then you have a fold, comes back. So you have exactly 2 solutions for any lambda. For dimension bigger than 8, there's only 1 solution, and there's an explosion here at the Pullin voltage. And then for n between 2 and 7, there's a minimal branch, and then you have a branch that goes like this, and then it goes back. Here, what this doesn't show you is that it keeps zigzagging around this line and goes to infinity. And I didn't understand where the dimension interfere, because after all, the nonlinearity is 1 over u squared. If you're dealing with u to power p, you know that the dimension intervenes via the Sobolev inequality. But here, it's 1 over u squared. The power is fixed. And then it helps when you have somebody like Louis Nuremberg visiting you, and I said, we're getting this. Where the dimension appears? And he said, check an old paper of Joseph and Lundgren in the early 70s, where they see where they see such pattern for the exponential nonlinearity. And that's how we really start realizing that there are some mathematics already done 30 years. It's the first time mathematics precedes the applications. But this is, the problem here is that this is for f is equal to 1, the permittivity profile is 1, and it's for a ball. And that's why you can use ODE method and the question is that do you have this situation for any domain? Okay, so again, in dimension 1, there's always 2 solutions. For each lambda, there's 2 solutions. And when lambda goes back to 0, the second solution hits 1. Okay, it becomes singular. For dimension bigger than 8, there's only 1 solution here, and then the solution is singular at the Pullin voltage. And for dimension between 2 and 7, there's 1 solution here. And so this is a solution with Morse index equal to 0. So ideally, the second branch here is going to be, these are the solutions with Morse index equal to 1. And then the third branch, solution Morse index equal to 2, etc. So as you go up higher, you're getting solutions with Morse index increasing. And at the limit here, you're going to 1 at the end, at the singular solution. And this is the Morse index is going to be infinity. So that's what essentially we'd like to prove, but for any domain. And this is interesting because to prove, essentially these things are, well, I'll tell you in a second which one is true in any domain or not. But to prove these kind of things, it took the kitchen sink of modern elliptic PDE. All the methods that were developed in elliptic PDE in the last 30, 40 years are needed to establish that such a bifurcation diagram essentially hold in higher demand, for general domain. That means the PDE aspect of this. So that's why I said, on the ball, you essentially have 2 solutions, and this on the ball. Extremal solutions is singular for n, the dimension bigger than 8. Now for the dimension between 2 and 7, here you take permittivity profiles that are quite general, and G is far away from 0, but you have x to the power alpha. And actually it can be 0 in a finite number of points. So if you take any permittivity profile, you can prove what Joseph and Lundgren proved for the ball. That means uniqueness for small lambda. See, now I'm looking at this branch, dimension between 2 and 7. That's a very robust configuration. So you notice that the branch doesn't come back to 0. So for small lambda, you have uniqueness. There's no solutions here besides the minimal solution. You can prove this, but it's not trivial. And then you can prove that around here you have essentially 2 solutions when you are close to the Pullin voltage, and then that there is a bifurcation diagram that changes, that turns infinitely, it starts at 0 and goes to the first bifurcation point, and then it bifurcates an infinite number of times, go all the way to the infinity going to 1. So you can prove these things, but these are many theorems and many pages here to prove this. But they are very interesting mathematics. Now, what's more interesting is what we've been doing the last 2 years. Now we're trying to deal with the fourth order. And here, the situation is much more intricate, but we have some recent progress where, see, here we say that the critical dimension is 8, because up to dimension 7, we have regularity for the Pullin voltage, but after dimension 8, the Pullin voltage is the Pullin solution is not is singular, yeah? It hits 1. So we say that 8 is a critical dimension for this problem. Now, when you go to the fourth order, we proved very recently that actually it's 9 which is a critical dimension. So when you add the fourth order operator, which is supposed to be a smoothing effect, you expect to have more regularity. All what this does is that it shifts the dimensions by 1. So before, for dimension 1, we had 2 solutions. Now, for dimension 1 and 2, that we have 2 solutions. And then, when we have regularity and the bifurcation, it's between dimensions 3 and 8, as opposed to 2 and 7. And then the extremal solution is singular for dimension bigger than 9. And this is quite intricate. So this is a new progress let me talk a bit about mathematics. You would like to prove that there is an infinite number of solutions, and the solution's Morse index is going to infinity. So we prove this theorem, that if you have a bunch of solutions, that if the solutions do not converge to a solution, that means the infinity norm go to 1. Remember, here infinity is 1. So this is a non-compactness here in an infinity norm. This is a non-compactness in the 3n over 2 norm. L 3n over 2 norm for 1 over 1 minus u. Okay, you're saying that u goes to 1, how fast u is going to 1. So you take 1 over 1 minus u, you take its LP power. So the critical power here is 3n over 2, where n is a dimension. And this is the Morse index is going to infinity. So these 3 statements are equivalent. We prove this. Okay, so in other words, if you fix the Morse index, you have compactness. Okay, so you have compactness of the solutions. If you say you take a bunch of solutions with Morse index at most 5, then you have convergence. That's a very, very nice theorem. And how do you prove it? To connect it with some familiar mathematics for the geometers, you assume that you don't have compactness, and you blow up the singularity, something that the geometric analyst taught us some time ago. And here, if you don't have compactness, that means u lambda n goes to 1, right? So you take this difference, which is epsilon n, and you blow up the solution with it, and this solution converts the solution to the space, to the solution of this equation at infinity. So that's a standard method. So you study how lack of compactness, how it gives you a solution for limiting equations at infinity. So now you look at this thing at infinity, and then you look for a Liouville theorem. Liouville theorem says, suppose you can prove that this thing doesn't have solutions at infinity, have only trivial solutions. So what does it mean? That means you have compactness. That means you cannot recover solutions like this. That means you have compactness. But this is a Liouville theorem. Nonlinear Liouville theorems are very tricky. I mean, we still don't know whether they have solutions. But we know that whether they have solutions or not, if you add some additional conditions. For example, we know for dimension between 2 and 7, we prove that this don't have stable solutions. Okay? So all the solutions, whether they exist or not, if you prove that all the solutions for this are stable, then if you have a solution coming from a blown up solutions on the bounded case that are stable, you know that they cannot converge to a stable solution here. Therefore, you have compactness. Okay? So these are Liouville theorems. These are Liouville theorems that, but with modulo Morse index that are now very, very popular. And on these last 2 days in the PDE seminar, we saw some talks from Norman Dancer and Du about these So they're becoming very powerful methods. Okay, so this is one aspect to prove compactness. Another thing that we discovered is when the permittivity profile is equal to 1, the critical dimension is 8. So you don't have compactness for dimension bigger than 8. But then it turned out if you put a permittivity profile, which is not 1, but x to the power alpha, and you increase alpha, then you recuperate compactness. Okay, so this is what this says. That if alpha is large, beyond this number, okay, then the problem restores regularity. Okay, so you always have regularity between dimension 1 and 7. But then, if you add a permittivity profile, which is power law, then you'll have compactness for any dimension. So it's the first time, I think, where this permittivity profile, or this term of the coefficient, was used to really change the critical dimension of an equation completely. So here are, for example, the dependence on alpha. So this is, for example, so for any dimension bigger than 2, if you take, you put the x to the power alpha, then you're back to the solution between 2 and 7. So this is between 2 and 7. This is a compactness case, right, where we have lots of solutions and we have regularity here. But now, if you put as x alpha alpha large, and even if the dimension is bigger than 8, you're back to compactness. This is a compact case. So this is phenomena that quickly, dynamic deflection, I don't have time. But here, the interest is, for the same Pullin voltage, if the voltage is below lambda star, then you have global convergence to the stationary solution that we talked about. If lambda bigger than lambda star, then you must touch down. You don't have, okay, so it touches 1 at some point. And then if lambda is equal to lambda star, you also have global convergence. But this is very tricky here. And this is the same Pullin voltage as a stationary case. What's interesting is that this means that you can have, if in dimension bigger than 8, since critical voltage is, the critical solution is singular, that means you have touchdown in infinite time. Okay, so this simple equation exhibits all the possibilities for touchdown: finite time, infinite time, or no touchdown at all, depending on this. But that's not what the engineers are interested in. They know that for large voltage, you have touchdown. But they're interested in the time to estimate how far, how long would it take before touchdown, and how the membrane geometry, and how the permittivity profile, and how the voltage that exceeds the Pullin voltage affects. So here's a nice estimate. Well, these are touchdowns that you could see. But then you can define the quenching time or touchdown time, which is the supremum last time where the supremum was strictly less than 1. We didn't have, okay? So you define this, and you try to study its dependence on lambda and domain and the permittivity profile. And you have nice estimates here. Remember this lambda 1 bar, lambda 2 bar that I introduced at the beginning, this upper estimates for the Pullin voltage. So if you are beyond them, then you have nice explicit ways to estimate the touchdown time. In general, we have this formula, which is not satisfactory because it's 1 over lambda minus lambda star is excess voltage, right? You're always assuming that you're beyond the Pullin voltage. Now, this is the nicest formula we obtained recently, which is what the conjecture is that the touchdown time is really bounded by 1 over the square root of the excess voltage, which is the optimal rate. Okay, so and I don't think I have time to show you how the singularity is proved, but in dimension bigger than 8. But for the second order, all what you need is the usual Hardy inequality, which is this. Okay? How you compare the Dirichlet integral, Dirichlet energy, to the integral of phi squared divided by x squared. Okay? So here, the stability at the extremal voltage is given by the Hardy inequality. And the best constant here tells you when the Hardy inequality holds, or when we have stability, and that's how you get the dimension 8. Okay, that's the classical Hardy inequality. It tells you when the extremal solution is stable. And that's how you get the singular and dimension bigger than 8. But for the fourth order, it turned out to be much harder. And this was established we established this only recently. Why is it much harder? This is the standard Hardy inequality for fourth order. This is Laplacian phi squared, and this is phi squared divided by x4. So we know what is the best constant is n minus 4 divided by 4, all of it squared. Okay? So, but this is not, it didn't turn out to be sufficient. You had to prove more sophisticated Hardy inequalities. So it turned out that to prove singularity for dimension bigger than 17, you have to prove this Hardy inequality actually these are called Hardy relic inequality. For dimension between 10 and 16, you have to prove this inequality. And for dimension 9, which is really the critical, you have to prove this and use Maple, etc., etc. So, and these are new Hardy inequalities obtained, that we had to prove for this problem. So, and that's how you prove singularity for dimension bigger than 9. So there, even applied problems come and give you very nice mathematical problems to work on. Thank you very much.
Any questions and remarks?
Too easy. Yes.
Are the engineers happy with your results?
Well, it's very interesting because that was the frustrating part. So the first model that he came up with was just the second order. Okay, and here we could do lots of things. Well, thanks to Joseph and Lundgren, and here mathematics we have lots of. But then once you give them all this, it's, oh no, the Laplacian is not enough. No, that you need bending. You have to add the bilaplacian. And that's why we started working on the bilaplacian and realized how little we know about this, and we can only give them results on the ball. And this is still, I think, it's wide open. And all engineering problems, bending is there. You cannot ignore the bilaplacian while mathematics is behind. But of course, then you talk to geometers. No, this is the wrong operator. It's a mean curvature. You should put mean curvature operator. That's how the membrane evolved. So one has now to deal with with mean curvature operator. And of course, some hardcore engineers are not interested in this because they don't think that the deflection goes vertically. That means so now you are looking for solutions from elasticity, from equation in elasticity, right? Where they are vector valued solutions. So when you consider that even the simplest problem in elasticity we don't understand, when you put this in 3 dimensions, it becomes horrible. You can't do anything about it. So that's why it's frustrating. You see that the mathematics still needs lots of development to catch even the most simple model.